Hi everyone, my name is Xinghe. I come from Hunan University. Today I present our paper about enabling energy-efficient DNA training on hybrid accelerators. This is a collaboration work from Hunan University, UC Merced, and Alibaba. As we know, DNA training can be extremely energy-consuming. For example, training BERT with 8 NVIDIA V100 GPUs for 12 days takes nearly 2.5 billion joules, which is almost equal to the average energy usage in a single-family home. The main reason for the large energy consumption of DNA training is the use of GPUs. GPU like V100 has a large thermal design power of 300 watts. In a typical training system, GPU is the most power-consuming hardware component in a machine, which can easily account for more than 90% of total system power. The prevalent method to lower GPU power consumption by scaling down GPU core frequency can cause large performance loss. We observed that over 30% performance loss when scaling down the V100 core frequency. For DNA training, GPU has become the predominant platform for DNA training due to its massive thread level, parallelism, and high memory bandwidth. However, GPU is too power hungry. In recent years, FPGA is emerging as an alternative because of power efficiency and high customizability, but it has lower operating frequency and memory bandwidth. Currently, the entire training process is assigned to run either on GPU or FPGA alone, which leaves the rich diversity of individual operations ignored. Due to the rich diversity of operations, some operations may have no demand of high thread level parallelism and memory bandwidth, which can be potentially offloaded to FPGA, while other operations can still run on GPU. Hence, we propose a system with hybrid accelerators to combine the strengths of both GPU and FPGA for DNA training. Overall, we aim to enable energy-efficient DNA training on such hybrid accelerator system. We target two common use scenarios in data centers. That is, saving energy as much as possible without training throughput loss, and meeting a strict power cap while maximizing throughput. Different hardware plays different role in this hybrid accelerator system. Specifically, GPU is used for performance acceleration. FPGA works as an accelerator of GPU to help lower the system power consumption. CPU is in charge of kernel allocation and scheduling. To use such hybrid accelerator for DNA training, we identify several fundamental challenges. The first challenge is how to avoid training throughput loss, because FPGA typically has lower operating frequency and memory bandwidth than GPU. The second challenge is how to schedule operations to minimize energy consumption or meet an enforced power cap. Because DNA training workload usually involve many types of operation, each operation has different choice of executing on the GPU or FPGA. For a specific operation, depending on the input, the operation also manifests varying computation and memory access patterns, leading to different choice of execution. So there's a large number of combined choice of executing operations. The third challenge is how to integrate and use FPGAs in the existing infrastructure of DNA frameworks. Such integration needs to meet two requirements. First, the framework needs to provide flexibility for fine-grained operation scheduling. Also, the framework needs to be FPGA architecture independent. However, the existing efforts such as OpenVINO and the leaf-flow cheat a collection of operations as a whole without per operation scheduling. Cheat cycle is tightly coupled with silenced FPGAs, which makes it difficult to use more broadly for other FPGAs. The first challenge is optimizing performance of an FPGA kernel is time-consuming, because the optimizing process involves lengthy placement and routing cycles to generate FPGA circuits. In this paper, we introduce a framework named hypertraining, which enables effective DNA training on hybrid GPU FPGA architectures. Hypertraining has underlying architectural complexities from users and automatically maps individual operations onto GPU and FPGA while meeting energy, power, and performance goals. The key enabling idea of hypertraining is to leverage a combination of offline parallelization, performance modeling, and online scheduling. The goals of parallelization are to drive our design on runtime schedule and provide insights on how to offload operations to GPUs and FPGA. We use a set of profiling tools for this purpose. We use PowerPlay Manager for FPGA power profiling and TF Profiler for time and operation dependency profiling. We also use NVProf for profiling with hardware counters. This table reports the profiling results of some of the representative operations. The first observation is for an operation with different inputs, the variance in power is large on GPU but small on FPGA. For example, for the operation matrix multiplication, its peak power variance across inputs on FPGA is much less than on GPU. And this observation suggests our performance models should include input information as model parameters. The second observation is different operations have different power consumption. Such difference is much bigger on GPU than on FPGA, which motivates us to use operation-specific modeling to estimate performance instead of building a generic model for all operations. And the third observation is running operations on FPGA always use less power than on GPU. As shown in the table, this is true for all operations. And this observation provides us useful hints on runtime scheduler. If there's no power cap, there's no need to consider the power consumption of operations on FPGA because running operations on FPGA always saves power. The fourth observation is some operations on FPGA can lead to comparable or even better performance on GPU. And we also observe these operations tend to have relatively small IPC and memory bandwidth utilization. And this observation gives us hints on which operation to select for running on FPGA. The memory bandwidth utilization and IPC of an operation running on GPU can be good indicators of whether running the operation on FPGA can lead to performance loss. Leveraging the metric of memory bandwidth utilization and IPC on GPU, we set up two thresholds for two metrics. If an operation whose memory bandwidth or IPC is smaller than the two threshold, it's regarded as a candidate to be offloaded to FPGA and then go through offline kernel optimization on FPGA. Using this threshold-based approach, we can eliminate unpromising operations to run on FPGA early on. After determining which operations to offload to the FPGA based on the workload characterization, we implement them in OpenCL and optimize their performance through design space exploration, critical path analysis, and the use of several other kernel optimization techniques. Many optimization parameters are available for FPGA kernel optimization, such as number of compute units, CMD width, the degree of loop unrolling, workgroup size, which forms a large design space because besides synthesizing an OpenCL kernel file to generate FPGA bitstream typically takes hours. Hence, exploring the design space is too time-consuming. We use performance models to estimate and compare the performance of various combinations. We introduce a new metric called the latency indicator. The performance model is input-aware and specific to each operation. Since the number of operations is limited, such operation-specific modeling is practical. We use the operation matrix multiplication as example below, and the modeling of other operations follow the same method. The numerator in the equation quantifies the total computation in the operation, and the work group size is the number of work items in the group. Larger work group size lead to higher performance, but subject to hardware constraints. And the Fmax is the FPGA operating frequency, which is a function of CPU, SIMD width, and loop unrolling degree. Overall, performance is related to Fmax and the input size, and Fmax works as a bridge to connect the three configuration parameters with the performance. For each combination, we can use the vendor compiler to get Fmax. Higher Fmax tends to have better performance. We designed two different scheduling strategies for two use cases. First, for case 1, the runtime system examines the task queue in TensorFlow. In the task queue, there are operations with dependency resolved and ready to launch. If GPU becomes idle, the runtime will schedule the operation to run GPU. If the FPGA becomes idle, the runtime will schedule the operation to FPGA. If the operation has multiple FPGA kernels, each corresponding to one type of input size, the runtime selects the best kernel to run based on the operation input. If there are only FPGA operations already in the queue, and at this time GPU is idle, FPGA is not idle, the runtime will run the operation on GPU without waiting. For the case 2, the runtime examines GPU power sensors and operations in the queue to get the current system power. If the peak power of an operation is less than the power cap minus current system power and the GPU becomes idle, the operation will be scheduled to GPU. If FPGA is idle and the GPU is not idle, the runtime will schedule the operation to run on FPGA, and also the best kernel will be selected. If there's no such operation, the runtime will wait until a new operation is ready, and this ensures that the system does not violate the power cap. We set up a hybrid accelerator system including 2 GPUs and 6 FPGAs. We use 6 DM models to evaluate hypertraining. And this figure compares GPU owning and GPU FPGA system in terms of training throughput and power consumption. Regarding performance, compared with GPU owning, hypertraining has no performance loss and even 3 to 24% improvement in throughput. And this performance improvement is because of two main reasons. First, after offloading some operations to FPGA, these operations no longer compete for GPU resources, such as memory bandwidth and GPU cores with other operations on GPU, and this allows operations that are not offloaded to FPGA to deliver higher performance on GPU. Second, the data movement time between GPU and FPGA is smaller than between CPU and GPU. Moreover, as operations are offloaded to FPGA, the data movement time may be partially overlapped by the runtime schedule. Regarding power consumption, GPU FPGA accelerator system with hypertraining consumes 23.3% less average power than GPU only. And this figure shows the improvement in energy efficiency and the reduction in data movement with hypertraining. Regarding energy efficiency, hypertraining achieves significant improvement. 44.3% on average. Compared with GPU only, the data movement time exposed to the critical path is reduced by 11.1% on average after some operations are offloaded to the FPGA. And in this paper, we use training throughput per watt as the metric for energy efficiency. And we also evaluate hyper training with power camping. And the above figures shows the runtime system power for 6 models under 230 watts power cap for GPU only, and GPU FPGA with hyper training. Compared to power management mechanism GPU, we can see that across the DNN models, hyper training consistently keeps the system power below the power cap. Besides, hyper training has 11.3% better throughput. And in all these models, hyper training has zero violation of the power cap. And here's the conclusion for this paper. And we show that DNA training using hybrid accelerators is promising. To make hybrid accelerators successful, we must consider runtime design and fine-grained workload characterization. And we also show that hypertraining can exploit a mix of GPUs and FPGAs at a fine granularity to achieve significant improvement in energy efficiency. Compared to the GPU-only system, hypertraining, DNA training with hypertraining can reduce the energy consumption by 40.8% on average and up to 59.7%. And also, there's not any loss in training throughput across DNA models. Thanks.